All right, welcome everybody. Today we're going to talk about section 4.6, and this is going to be an introduction to graphing polynomials. Now, the truth is, your ability to accurately sketch the graph of a polynomial is the ultimate end goal. So you're not actually going to be creating any graphs today, but you are, however, going to be learning and relearning the skills you need to do so. And I'm going to give you some graphs, and you're going to kind of work in reverse to find the equation, all of which should help you towards the ultimate goal, which is to create the graph on your own without the use of a graphing utility. So a couple things that we want to remind ourselves of first, the fundamental theorem of algebra, we have kind of seen and heard about this a couple of different times now, but just as a reminder, a polynomial with degree n will have n x-intercepts or n roots. An example of that is, let's say that the n is 2, so 3x squared. There has to be exactly 2 x-intercepts or 2 roots, whereas something like x to the third minus 36x, because that's to the third power, there has to be exactly 3 x-intercepts or roots. We've kind of, again, been talking about graphically, what does it mean to be an x-intercept? So let's just make sure that we're aware that an x-intercept is a point on the graph where the polynomial crosses the x-axis. If you are trying to solve from an equation for the x-intercepts, you have to set the function or the y equal to 0, and then you have to solve using the zero product property. Just a couple of visuals here to help remind us. So first of all, we have a quadratic, which hopefully you remember the vocab word, which means degree 2, which means it's going to cross the x-axis exactly twice. Then here in the middle, we have a cubic, which of course means degree 3, which means it has to have 3 roots and cross exactly 3 times. So 1, 2, 3. Then over here at the end, we have a fourth power, which is a quartic. So we have to cross exactly 4 times. And here's 1, 2, 3, and 4. What we need to start asking ourselves is, what is going to happen at those x-intercepts? Is it going to go through the x-axis? Is it going to just touch it and not go through? And so that's all the things we have to kind of get the background on before we can actually create the graph. So we're going to start off nice and simple with a skill that we actually already should know. I'm going to ask you to find the roots of the polynomial function. Make sure that your number of answers is equal to the degree of the polynomial. Now notice that in these 6 problems, they are either equal to y equals, or they're f of x or g of x or some function. If you are trying to find the roots of a polynomial, you have to start by setting the equation equal to 0. So if it's a y equals, you're going to set the y equals. If it's a g of x equals, you're going to set the whole g of x equals. In order to actually solve for something, you have to start by setting it equal to 0. Now, every time there is an x, that is going to give you one of the roots or one of the solutions. And hopefully you remember that most times it's the opposite. So in the first equation here, so x plus 1 equals 0. In order to solve for x, you would subtract the 1, which means that for number 1, x is equal to negative 1. That's it. It's only x to the first power, which means there's only one solution. In number 2, there is again only one solution, but we would first have to add the 3, then divide by 2, which is why we would say that x is equal to 3 over 2. Something a little bit interesting here in number 3, you now have the equation 0 is equal to 7. Well, there are no variables. So if there are no variables, then there can't be any solutions. Additionally, is 0 equal to 7? It is not. That is not true. So if the question is to find the roots and you can't find any, then the answer is none. As a reminder, that is because this is a constant function. So the constant function in this case does not cross through the x-axis, which means there are no x-intercepts, and therefore there are no roots. If you take a look at something like number 4, each of these different parentheses, or simply each of these different variables, has to give you a different solution. Whenever you have just a lonely little x, if you set x equal to 0, you just get an answer of 0. If you set x plus 1 equal to 0, you're going to get negative 1. If you set x minus 3 equal to 0, you're going to get a value of 3. Because this is x to the first, x to the first, and x to the first, that has a degree total of 3, which means there has to be exactly 3 solutions, and here they are. In the next one, 3x plus 1, if you set that equal to 0, you would first subtract the 1 and then divide by 3. Here in the orange, if you were to set that equal to 0, and again, you can do that on the other side if it's helpful, you would first have to add the 3 and then divide by 4. So again, because this is x to the first and x to the first, you have a total of a degree 2, which means you have to have 2 solutions. Finally, for this last one, 3x is its own quantity. X plus 8 is its other quantity. If you were to set 3x equal to 0, you would divide that 3 away and simply be left with a 0. Whereas if you set x plus 8 equal to 0, you would get an answer of negative 8. So hopefully everything in these first 6 examples makes sense. Hopefully it's not even new, but you have to have as many solutions as the degree. And if you have factored form, which these are, you're going to set each parentheses equal to 0 and solve. What happens if something is an answer more than once? Your teacher may or may not have told you how to indicate that to this point, but we now are going to have a formal way to do it using something called multiplicity. So if a factor appears more than once, that is called multiplicity. Multiplicity is how often a certain root is part of the factoring, and the main reason why it's so important is because of the graph. Something with a multiplicity 1 does not behave the same way as a multiplicity 2, does not behave the same way as a multiplicity 3. So go ahead and take a look at this first example here. You have an x minus 5 cubed, you have an x plus 7 to the first, and you have an x minus 1 squared. And again, if you need to remind yourself that this is to the first power, feel free to add those in wherever needed. They start by just giving you a little reminder. You could take that x minus 5 cubed and you could write it as 3 different copies. You can take the x minus 1 squared and write it as 2 different copies. That's kind of what we've been doing for now. But the truth is we want to have a little bit of a time saver. So however many times you can write that factor, or whatever the degree is, that is going to be the root's multiplicity. So if you take the x minus 5 and you set it equal to 0, you're going to get the opposite answer of positive 5. And then because of the fact that there are 3 copies, and the fact that it's to the third power, oops, sorry, those should be with the x's, so 1, 1, 1. So because there are 3 factors, that means that the root is going to have a multiplicity of 3. For the x plus 7, there is only 1 copy. This is x to the first. So the answer is going to be the opposite, which would be negative 7, but it's only going to have a multiplicity of 1 because it only appears once. Then for the x minus 1s, so for the x minus 1s, because it appears twice, that means that you are going to have a root that is the positive version. And because there are 2 factors, that means that we're going to say that it has a multiplicity of 2. So what does it mean if it has a multiplicity of 1, 2, or 3? We're going to get to that in a minute. But for now, you just have to be able to recognize that something does have those multiplicities. And then to abbreviate, we're going to just go ahead and use the letter m. So take a look at the next set of problems. For each function, determine the roots and their multiplicity. So when you're determining the roots, I want you to tell me the x equals. You're going to say m1 if it's multiplicity 1. You're going to say m2 if it's multiplicity 2. And you're going to say m3 if it's multiplicity 3. So let's go ahead and take a look at number 1. So it's already set equal to 0 for us, which is good. If I look at x plus 4, that's going to give me an answer of negative 4. X minus 4 is going to give me an answer of 4. X plus 2 is going to give me an answer of negative 2. Because each of these factors is only to the first power, these are all going to be multiplicity 1. The truth is, if they're multiplicity 1, you can just say nothing. The multiplicity 1 would be implied. But for now, when you're kind of just getting started, you might want to put it just so that you don't forget. But again, you could just put nothing, and then multiplicity 1 is implied. Let's take a look at the next one. So starting with the x plus 3, that's going to give you the opposite answer of negative 3. Because it's to the third power, that's how you know that this is going to be negative 3, and it's going to be m3. Then you have 5x minus 2. If you set that equal to 0, you're going to add the 2 and divide by 5. Because it's to the first power, that's going to be an m1. Again, having those multiplicities means something, which we're going to get to shortly, but for now, you just have to be able to recognize it. So over here in number 3, starting with this negative x squared. Again, a negative is just a negative, but it doesn't tell us anything about what a 0 is. So you're kind of just going to disregard that negative. So that x squared, that's essentially x times x, which means that 0 is the answer, but because it's a squared, that's an m2. Then x minus 4 squared means that 4 is an answer, m2. And x plus 1 means that negative 1 is an answer with just m1. It should get faster, it should get easier, dare I say even fun. So in number 4, x minus 4 squared, 4 is an answer, and that's an m2. X plus 1, negative 1, m1. For number 5, the 5 out front, if you were to set 5x squared equal to 0, the 5 would divide away. So the 5 is important for other reasons, but doesn't tell us anything about what the x's are. So in this case, if you just have x squared, that means that 0 is an answer, but the squared means it's m2. Then negative 3, m1, and negative 5, m2. Just to make sure we've got it, take a look at number 6. Again, whenever you have something on the outside with no plus or minus in the middle, you would essentially divide that negative 3 away. So even though it does mean something, it doesn't affect the zeros. So that x squared means that 0 is an answer, m2. If you set 2x plus 1 equal to 0, you would get negative 1 over 2, and that's an m2, followed by negative 2, m1. So now that we understand how to look at an equation and identify the roots and their multiplicity, the next thing is going to ask you to work exactly in reverse. So if I give you the roots and their multiplicity, you're going to write me an equation. Notice that you're going to write it in factored form, which means don't multiply it out. It'll take you a really long time if you try to multiply it out, so don't do that. So here for number 1, x equals 0, 1, and 2. And again, if there's no multiplicity stated, you're going to assume that it's a 1. So you have to call your equation something, y equals f of x equals, whatever you prefer. And then each of these zeros becomes a matching factor. This 0 means you have to have an x. This 1 means you have to have an x minus 1. And this 2 means you have to have an x minus 2. Assume that all the multiplicities are equal to 1, which means that's all you're looking for. This is factored form, which again means don't multiply it out. Here in number 2, let's call this one f of x, just to switch it up. Remember, it doesn't matter. The negative 2 would become x plus 2, followed by x plus 4, followed by x minus 6. And again, no need to multiply it out. That's not what it's asking you to do. So everything so far has been a multiplicity of 1, but now we're going to see a little bit of a change. So starting with 1 and 7 are going to both have a multiplicity. So x equals 1, that's 1 root. Then x equals 7 with a multiplicity of 2, and then negative 5 with a multiplicity of 2. So when I go to write this, and again, I'll call this one y equals, just the lonely 1, that's going to be x minus 1. The 7 multiplicity of 2, you're going to write that as x minus 7, and then a squared. The multiplicity of 2 for 5 is going to be x plus 5, and you're going to write it as a squared. Just a note about order here. It doesn't matter what order you list the factors in. I would just go in the order that they were given, because why not? But the only thing that isn't necessarily wrong if you don't, but it's just considered proper, if you have just a single x, that generally does go in the front. So you should put that in the front, but otherwise the order doesn't matter. Over here for number 4, you have 0 multiplicity of 2, followed by a 6 multiplicity of 3. So again, I'll call this one f of x, just to switch things up. If you get a value of 0, that means you have to have an x. If there's a multiplicity of 2, you've got to square it. In order for you to have an answer of 6, you'd have to have x minus 6. In order for it to have a multiplicity of 3, you would have to cube it. So just take a second and digest everything we've done so far. We reminded ourselves how to solve for the roots. We learned about how you identify multiplicity. And then given a multiplicity and a root, we went ahead and were able to write the equation. So now kind of the most important thing is, how does multiplicity affect the graph? You've actually seen this before, but you never quite, drilled down and really defined it. So let's go ahead and do that now. There are 3 different types of multiplicities you're going to be responsible for. Something that is multiplicity 1 to the first power, something that is multiplicity 2 to the second power, and multiplicity 3 to the third power. So these graphs show you an example of what happens, and let's make sure that we can identify it. So here at A, this would be a multiplicity 1. And the way that you would describe that is that the graph is crossing the x-axis. It either comes from the bottom to the top or from the top to the bottom. Whereas over here at A, this is considered to be a multiplicity 2. And instead of crossing the x-axis, you're actually going to write that as a bounce. Notice that it touches the A, but it doesn't actually go through. It goes back in the same direction. Finally, this over here is considered to be an M3, and at an M3, the graph flattens and crosses. So you'll see kind of over exaggerations about that to make sure that you can recognize it, but the best way that I would describe it is that the graph flattens and crosses. So again, these are the key things we're looking for. Does it cross? Does it bounce? Or does it flatten and then cross? Again, just to reiterate, here, this x minus a to the first, x minus a squared, and x minus a cubed, those are all the factors. If you were actually solving for the roots, it would be x equals a and multiplicity 1, and then x equals a with multiplicity 2, and then x equals a with multiplicity 3. So we're going to put all that together in just a minute, but the last thing we need to review is we need to remind ourselves about the 4 types of end behavior. So you've seen the end behavior combinations a couple of times now. It's especially important tomorrow, but it is useful for today as well. So just a quick reminder, end behavior, of course, tells you what happens at the end, specifically what's happening as x approaches positive infinity and as it approaches negative infinity. It is determined by 2 things: the degree of the function, whether it's odd or even, and the sign of the leading coefficient, whether it's positive or negative. We describe them using up and down, and again, it describes the left and right hand behavior of the graph. So over here are the 4 combinations for end behavior. Again, you should have them written down several places, but just in case you need another reminder, even positive would be up, up, even negative would be down, down, odd positive would be down, up, and odd negative would be up, down. So as we work through the remainder of this lesson, refer to these as needed. And then here's the ultimate goal for today. So again, notice that for each of these problems, I have given you the graph. I'm not asking you to graph anything yet. That's not till the next lesson. What I am asking you to do is tell me things about the graph based on the things that we have done so far in this lesson. So a few things to point out here. Number 1, you're going to give me the answer in factored form. That means do not multiply it out. Secondly, it is possible that any of these graphs could have a leading coefficient other than 1 or negative 1. If we wanted to find out for sure, it's a bunch of extra steps. We're not actually going to do that right now, but what we are going to do is account for this possibility, which means we're going to put an A in front of each answer, meaning that A could be anything. It could be a fraction or a decimal or a really big number. At some point, we will actually find it, but for now, we're just going to remind ourselves that it's there. So let me go ahead and show you the process that you should do to answer a question like this. So again, the ultimate goal is you're trying to find factored form of the equation, and I have set it up in a way that I think helps. So starting with the end behavior, you're going to look at the left, you're going to look at the right. Whichever way it's pointing to the left side, whichever way it's pointing to the right side, you're going to go ahead and tell me that end behavior, which in this case is down, up. If you look at the top of the page for the combination of down, up, that only happens if something is odd, positive. So when I say, what is the sign of the leading coefficient? It has to be positive because you just told me that it was. Once you figure out that it has to be positive, the first thing you're going to do is you're going to say y equals, and you're going to say positive a. Positive because it has to be a positive, and the A means it could be anything. +4, +50, +60. You don't actually have to find A for now. You just have to know that it's there. Then look at the graph. Everywhere it crosses the x-axis, that's an x-intercept, which means it's a root. If it actually crosses the x-axis here, here, and here, you're going to label those as the M1s. That's a multiplicity 1 and a multiplicity 1 and a multiplicity 1. Remember, crossing the x-axis, that means it's an M1. Look at what's happening over here at 1, though. That's not a cross, that's a bounce, which means you're going to call that an M2. So here, you're just going to go ahead and list those out. And I would just go from left to right. So you're going to say x equals -2 M1, -1 M1, 0 M1, and then 1 M2. Guess what? Here's where you can kind of do a quick check. The whole reason why you told me that this was supposed to be odd is because if you add up all those multiplicities, it has to wind up being an odd number. So 1 + 1 + 1 + 2, that's 5, which is odd. That's how you know you're on the right track. Now, last but not least, each of these roots and their multiplicity has to now become a factor. And again, order doesn't matter, except if you have a 0, you should put that first. So that 0 means you need an x. Then the -2 becomes x + 2. The -1 becomes x + 1. And the 1 becomes x - 1, and you have to square it because of the multiplicity. So this is the final product that you are looking for. It's possible that after time, you'll be able to do that more quickly without actually showing all the steps. But for now, while you're just getting started, I don't see how it could hurt. Let's go ahead and take a look at number 2. So again, the first thing you're going to do is you're going to look at the left side, you're going to look at the right side, and you're going to try to figure out the end behavior. Hopefully, you would agree that that is up, up. If you look above at the table, the only way that that occurs is if it's even positive. So once you deduce that it's positive, that means the sign of the leading coefficient is positive, and you're going to say y equals +A. Remember, A could be anything. Then you're going to go from left to right. Anywhere the graph crosses, you're going to write an M1. Anywhere it bounces, you're going to say an M2. And anywhere it crosses, you're going to say an M1. Again, we're going to get to multiplicity 3s in a minute. So the roots and their multiplicity from left to right, it's -2 M1, -1 M2, and +2 M1. If you want to be careful, go ahead and add up the multiplicities. That's 4. Is it even? It is. So now each of those roots has to become a factor. Because there's no 0, order doesn't matter. So the -2 becomes x + 2. The -1 becomes x + 1, which is a multiplicity of 2, and then x - 2, again, with a multiplicity of 1. So this is what you are looking at for your final answer. And again, factored form means do not multiply it out. Doesn't really get too much harder than that, except for a couple of small things. So here for number 3, look at the left side, look at the right side. Hopefully you can agree that that is end behavior down, down. That only happens if it is even and negative. So this is the first negative that we've seen today, which means that the sign of the leading coefficient is negative. All that means is that when you say y equals, you're going to say -A instead of +A. That's it. Now go from left to right. If there's a cross, you're going to call that an M1, cross, M1, bounce, M2. So list them out. X equals -2 M1, then 0 M1, followed by 2 M2. Double check, 2 + 1 + 1, that's an even number. Then when you go to write your equation, remember order doesn't matter, except if you have a 0, you really should put that x first. And then x + 2 and x - 2 squared will finish you off. If you've been wondering, well, what does an M3 look like? Well, wait no further. We're going to have one here in number 4. So step 1, again, end behavior, down, up. Down, up only happens if it's odd positive. So if it's odd positive, you know the sign of the leading coefficient is positive. And if the sign of the leading coefficient is positive, it means the first thing you're going to write in your answer is y equals positive a. Technically, you don't have to put the positive there. I mean, we know it's positive, but for now, I just want you to realize it could be positive or negative. So I'm just writing it as a placeholder. So then as you go to look for your x-intercepts, here at -4, see how the graph is changing from being on the negative side to the positive side, but see how there at -4, it's kind of getting super flat on both sides. If you go back and look at an M1, I think you can understand why that's clearly just going through, nothing strange about it. Whereas if you look carefully at -4, this is clearly a flattened situation. So you're going to say that that's an M3. And then this looks like a bounce, which means an M2. Just so you know, after multiplicity 3, there are still behaviors. They kind of start repeating for multiplicity 4 and 5, but you're only responsible up to 3. So you're going to go ahead and list them. So you're going to say that x equals -4 M3 for the flatten, and then +3 M2. Better safe than sorry. 3 plus 2 is 5, which is odd. That's good. And then for your final answer here, if you want -4 to be an answer, you're going to say x plus 4, and that's going to have to be cubed. And then you're going to have to say x minus 3, and that's going to have to be squared. So lots of important information that we went over today. All of this is building you up towards your ability to create a graph from scratch, but we're going to go ahead and save that for next time. So thanks very much for tuning in, guys, and we will catch you next time.